Hey everyone, it's Allison here for another science and engineering chat. And this time we're going to be talking about rockets, specifically rockets that go to space and deliver things like satellites and astronauts to space. It's going to wait a little bit for people to start joining. It's a minute or two early. I'm actually out here on my sun porch this time. We'll see how that works. The lighting seems to be better. If the lighting changes, it's because it's the sun's going in and out of the clouds, so we'll just have to work with that. I also got a little holder for my phone, so hopefully speakers. Waiting for more people to join. And my cat has joined me out here as well. So he's down here watching birds. Let me see if I can give you a picture here of Tiki. Tiki is my cat. There's Tiki. He's enjoying himself out here. So we only have one person watching so far. Oh no. It's 4 o'clock now, so we'll wait a little bit longer for people to join. And if you have questions, either put them in the chat now, or you can wait until our question and answer session. I'm going to have the first part of it, probably a little bit more than half. First part of it as a chat just going over rockets. It's aimed for kindergarten through 5th grade, but anyone can watch. And then we're going to have a quick question and answer session like we normally do. And then we're going to do a math problem involving rockets for the 6th through 12th graders. And I know that the math involves variables, which I know some middle schoolers may not be in, to that point yet in their studies. But if you aren't, just go ahead and follow along. I also have some links to websites that I'm going to be posting in the comments or the video description if you're watching this on YouTube. And those links are to a bunch of different websites that you can check out, and they'll relate to the topic and will be all about rockets. So, all right, let's go ahead and get started. It says I still only have one viewer, but we'll go ahead. All right, so rockets, specifically rockets that go to space. First of all, what makes a rocket a rocket? A rocket is not a plane, it's not a balloon, it's not a glider. The thing that's specific to rockets is they rely on thrust from an engine and expending fuel to get them up into space. So there's thrust going out the back of the rocket because you're forcing fuel out the back of the rocket. And oh hey Jersey, there's 2 people now, yay! And that thrust is propelling you forward, or in this case, up. So you want to get out of Earth's gravity well. In the last session we were discussing black holes, but we also did a little bit of an introduction to gravity. And so the Earth has gravity. You have to fight that gravity to get up into space, and that's what rockets help us do. Rockets usually use combustion in order to create this thrust. So combustion is when you have a chemical reaction that takes place and it catches on fire, so it combusts. And usually rockets have some sort of a tank that's full of this combustible fuel, and when you light it on fire, it creates a lot of hot gas. And that hot gas is coming out of the back of the rocket, and that's what propels you upward. There's a lot of energy in a really tight space, and that helps to create the energy that you need in order to break Earth's gravity, or to break free of Earth's gravity. This is related to, if you've studied it, Newton's third law, which says that every action has an equal and opposite reaction. So in order to get the reaction of you ending up in space, you have to have the action of that hot gas pushing against, the weight of your entire rocket. So you have to have your thrust be more than the weight of the rocket in order to get through the atmosphere and into the space environment. So I want to take you over to my easel of awesome, and we're going to take a look at the different parts of a rocket. So come with me over here. Once again, I wrote backwards for you guys, so if it looks a little bit odd, it's because it was written backwards. All right, let me get my little pointer here. All right, so here's my rocket. I've got the hot gas coming out the back of the rocket, and I'm moving my rocket forward or upwards into space. So we got, let's start at the bottom. Let's start at the bottom and go up, because that's usually how stages and stuff drop off of a rocket. All right, so at the end of your rocket fuel tanks, you have a nozzle. And this nozzle is really important to adjust the speed of the stuff coming out. So you can have different rocket shapes, nozzle shapes, and the shape of that nozzle really affects the velocity, the speed and direction of the stuff coming out the back. And so there's a lot of math and equations and things that you can use to get the correct shaped nozzle for the type of flow that you want out the back of your rocket. And then you can see there's a couple of different types of rocket tanks here. I've got these tanks on the side. I don't know if you've ever seen pictures. I'll show you a picture later, but if you've ever seen pictures of the space shuttle, when the space shuttle is on the pad, it's got this main orange thing, that's the main tank, and then it's got these little smaller white things on the sides that look kind of like this. And those are called SRBs, or solid rocket boosters. And they have a different type of fuel than the fuel that's in the main tank. And we'll get into the types of fuel later, because they're really cool. So we got two side tanks here, and once you get past the first phase of your flight into space, you don't need as much fuel to keep going. So the solid rocket boosters actually drop off of the rocket. You'll see them, if you watch a launch, you'll see them kind of like fall off to the side because they're empty and they don't need it anymore. They don't need that mass attached to their rocket, because it's only going to cause it to, it's only going to hold it back. So they drop that mass off. These solid rocket boosters detach and they fall off as it's going through space. All right, so we got the solid rocket boosters. They came off towards the ground. Now we have the first stage. And the first stage is the part that gets you out of most of Earth's gravity. Gravity decreases as you get further away from the planet or the moon or asteroid or whatever. Gravity decreases exponentially as you get away from that body. So you need more fuel towards the surface, and you need less of it as you get further away. So the first stage has a lot of fuel in it. Then that stage drops off, it separates. And then you light the second stage. The second stage is usually after you're out of most of the atmosphere, and you just need that extra little kick to get you into orbit. And then finally we have the nose cone, which is also sometimes called the fairing. And this is where all of our science happens. So this is where we've got the satellite or the astronauts in their little capsule. Look how small the nose cone is compared to all of the other parts. The nose cone is actually, even though it's the thing that we're trying to get into space, it's very small compared to all of this fuel that you need in order to get it into orbit. And so If you want to get something that is, for example, two humans in their capsule and in a lander to the moon, you need a giant rocket in order to get all of that mass off of the Earth. All right, so let's come back over here. All right, the next thing I want to talk about is the types of fuel that you can use in a rocket. There's two main categories with like a little bit of a side category of a combination of both of these categories. And the two categories are solid rockets, which use solid fuel, and then liquid rockets, which use liquid fuel. And combinations of those two can also be used, like with the solid rocket boosters that kind of help get you into space, and then you have the liquid one to get you the rest of the way there. So solid rocket boosters are made of solid fuels that are kind of like packed into the sides of that cylinder of the fuel tank. And you can pack them in different ways in order to get a better burn rate. So some of them have a little hollow piece in the middle. Some of them have like a little hollow flower shaped piece in the middle. You can get really creative with the different kinds of shapes for solid rockets. They're less efficient than liquid rockets, and you also can't stop them once they're lit. Like if you want to stop after lighting a solid rocket booster, like good luck. You can't. You just have to wait until it's done burning. You can't stop a solid rocket once it gets going. There are some rockets that are just solid rockets. For example, we use sounding rockets, which are ones that go up very briefly into space and then come back down for missions that only need to spend a couple of minutes in space to get the science they need. We launched those on solid rockets, and they're actually left over from the Cold War. They make new ones, but the original sounding rockets were ones that were left over from the Cold War, and they just said, hey, we're not using these, let's put some science on them. And so there are things like the Black Brant, the Oriole, out of Wallops Island, which is only about. So that's pretty cool if you ever go to Wallops Island. Not currently, because we're supposed to stay in our houses. But once you're able to, you can go to Wallops Island for a rocket launch, and you can see one going into space, which is pretty cool. The other type of fuel is a liquid fuel. Now these are really interesting because some of the liquid are cryogenic. You have to keep them very, very cold in order for them to work. Some of them, if you bump them too hard, they explode. And some of them, if you expose them to their oxidizer, then they instantly ignite. And that's what you want inside of a rocket. You have your fuel tank and your oxidizer tank. So you might, for example, have liquid hydrogen as your fuel, and you might have liquid oxygen or LOX as your oxidizer, and then you have a mixture of the two in the right percentage of each one to get the optimal burn rate, and then you send that through the engine, and that is what ignites and burns up. The good thing about liquid rockets is you can stop them. You can shut the valve and the fuel or oxidizer stops flowing, and you can shut off the rocket. So, for example, if you have a rocket that is on the pad and they discover that something is wrong, they can stop the countdown. Or I guess if you have a solid rocket booster, you can't attach, you have to burn through that. But if you needed to abort a launch for a liquid-fueled rocket, you could shut it off. There's also, as I said, combinations of the two, and there's limitless combinations of what you can use. But the most important thing is you have to have enough fuel for the mass of the thing that you're trying to send into space. All right, so I have a little activity before I get into orbit stuff. I have a little activity to show you the action and reaction that's happening when you have some compressed, in this case air, but some compressed fuel inside of a rocket and it creates thrust, and how it creates movement in the opposite direction. So you can do this at home. If you have a balloon and a straw, and you can also have this activity. So come with me, we're gonna go over here. I have this set up in this corner here. All right, we got a piece of straw. Whee! That is strung on this string. And I tried to keep the string pretty much level, so there's no going downhill that's helping. But we're gonna drag this all the way up here, and I'm gonna blow up the balloon. All right, so we got our balloon on a straw. This part at the end is gonna be the nozzle, right? Because we're having the in this case, compressed air come out the back. And so it's going to shoot forwards. All right, so I'll try and get on this side so you can see what's happening here. There we go. All right, 3, 2, 1. Lift off! We'll try that again because it's really fun. So you can do this in your room. You can create several of these and have like a flight of rockets. Tape's coming off. Oh no. There we go. All right, I'll do this again. Ready? 3, 2, 1. Blast off! See what happens if you put more air in the balloon? What happens if you put less air in the balloon? Also, you can try taping different things to the balloon. So what happens if you tape like a couple of marbles to the balloon? Does it go as far? Does it not go as far? What if you blew the balloon up more with the marbles attached? How far does it go then? So try it yourself, see what happens. My cat is so interested in this. You see a rocket? Every time I do that, he's just like, okay, so let's go over how does a rocket reach orbit. So I mentioned that it has to get, but how does it stay in orbit once it's up there? We have sounding rockets, which go up and come back down, but how do we get one to go up and stay up? You know, how do we deliver satellites to orbit? So I have my little picture here. All right, so we got this little kind of Goldilocks situation here. So this is what happens when your rocket is too slow leaving Earth. You're too slow to break out of that gravity well. Your rocket goes up off the surface. It maybe reaches the edge of space. Maybe it stays in the atmosphere. Maybe this is a model rocket that you launch out of your backyard. It goes up and it comes down. Gravity, right? It goes down. If you have a rocket that has too much velocity when it gets out there, if you go too fast, your rocket leaves the surface of Earth and then just keeps going. It doesn't enter orbit because you're going too fast. You have too much energy. And so you leave the gravity well entirely, and you're off to someplace in space. Mars, the edge of the galaxy, wherever you end up. But your spacecraft leaves Earth, and it doesn't come back. That's when you're going too fast. Here's our third example, where we're going just the right speed. What happens is you leave Earth, and if you hit the right speed for that distance away from Earth, you actually continuously fall towards the Earth, but you never get there. So an orbit is really a spacecraft that is falling towards Earth continuously and just never reaches the surface because it has enough speed to cancel out the force of gravity. Now there's other things that are acting on a spacecraft, and so most spacecraft's orbits decay over time, especially if they're close to Earth. Things like drag from the atmosphere, even though there's very, very little atmosphere in the space around Earth. Like the atmosphere doesn't really have an edge. There's no real, oh, we're in the atmosphere and I can do all the things that I do in the atmosphere. Oh, and if I go 1 inch this way, I'm out of the atmosphere. It doesn't work like that. It's kind of like slowly, you know, there's slowly fewer and fewer and fewer molecules until it doesn't really matter anymore. And so you can be in an orbit, like for example, the International Space Station. You can be in that orbit and have to keep boosting your orbit. Like you have to keep boosting your spacecraft because your drag from those little air molecules hitting your spacecraft are slowly you're making you slower and slower and slower, and so you drop your orbit. And that's how you get orbital decay. We won't really go into that much here because this is still about rockets, which is getting out of the atmosphere. But that's something that you have to think about when you're launching something into space. And just for some fun numbers, the speed that you have to be going in order to stay at 300 kilometers up, which is the orbital altitude of the International Space Station, is 28,000 kilometers per hour. That's a lot. 28,000 kilometers per hour. And so you have to attain really big speeds in order to stay in orbit. All right, so some famous rockets. Before we get into question and answers, I want to show you some famous rockets. One of the most famous rockets is the Saturn V. And you might recognize this one because this is the one that took people to the moon. Oh, reflections. There we go. That is the Saturn V rocket. And if you want some scale, that's a person down at the bottom there. The thing it's mounted on is called the crawler. That's how they get it to the launch pad because you can't carry it. You have to crawl it there. And they still have the crawlers. That's still how they get things to and from launch pads down there at Kennedy Space Center. But there's the Saturn V. That's the largest rocket that we ever made in the US. The Russian spacecraft that took Russian astronauts to the moon is the Soyuz rocket, and there's multiple Soyuz rockets. It's kind of like there's multiple Toyotas. Like you got the Corolla and you got the so like there's multiple Soyuz rockets at different sizes, but they had a really big one, and they're still making them, and so they've got smaller ones. It's actually the most used rocket in the world. That line of rockets. Here is a rocket that people who grew up in the 90s and 2000s are very familiar with. This is the Space Shuttle. This was the workhorse that got the International Space Station in orbit. And if anyone has questions about the International Space Station, it's still in orbit. I mean, there's still astronauts up there every single day doing science. They get up there on a Soyuz rocket right now, but they in the 90s and 80s, 90s, and 2000s they used this, which is the Space Shuttle, and so it's got 2 solid rocket boosters, and I know this is backwards. It's got the main tank, which is that big orange one in the middle, and then the shuttle itself was actually also a return vehicle, so you could reuse this. And this is a common theme in space travel, is they wanted to reuse things because it's very, very expensive to fly something like this. And so you see it has wings on it. Now those wings don't actually provide a whole lot of lift. People who have piloted the space shuttle have said it flies like a brick. You are basically just guiding a brick to the ground as slowly as you can. And so it has parachutes, like these parachutes that pop out of the back of it, and helped to slow it when it was actually on the ground. But the wings act more like as stability fins. And so you could keep it from, flipping around, and you could keep it kind of wheels down as it was being guided onto the tarmac. It lands like a plane. And then they could reuse it. Another one that is reusable, and this one's really cool. I have a video for this one. This one is the Falcon 9. It's developed by SpaceX, and this one's a little bit newer. This one is, oh gosh, it's gotta wait for the advertisement. This one is being produced to take supplies to the International Space Station to put things in orbit, like our science satellites and that sort of thing. Once it's done with the advertisement, I can show you. Okay, here we go. This is the first stage. Remember I said the first stage drops off? You can see it. There we go. This is the first stage of the rocket landing on a barge in the middle of the ocean. This is incredible. No one had ever attempted to recover a first stage in pristine condition before. First stages could be recovered from the ocean, but they were full of salt water. And this one is actually got guidance rockets that guide it into a standing position on a floating barge. That is incredible. Humans aren't guiding this, it's a computer. And it just kind of steers itself right back down to Earth after dropping off of the second stage. Remember I said there's a first stage and a second stage and then the actual payload. So that took a long time to develop. There were several videos which were just crashing right into the barge or missing the barge or it kind of landing and skidding off of the barge because it's the ocean. You have to account for it rising and settling in the ocean and like tilting. But it's amazing what they've done with this reusable stage that they can then fill with fuel and fly again. And then finally, I've got one that's called the Falcon Heavy. When I first heard of this, I thought this was ridiculous because it's a bunch of Falcon 9s strapped together, basically. But the Falcon Heavy is one that is, let me see if I can make this picture bigger. There we go. It's one that may be used to send astronauts to the moon again, or to the space station, or to Mars. And you can see it's got a whole bunch of boosters kind of strapped together at the bottom there. And it's got something like more than 10 nozzles at the bottom. It's like 25 or something. and they're all kind of strapped together. And they bring whatever it is, the spacecraft or the astronauts to wherever they need to be in space. And that one is kind of still in development. It's lifted off, but they're still improving it. So those are some examples of some really cool rockets. Before I get into the part for the 6th through 12th graders, which is kind of the more math problem aspect of it. Does anyone have any questions about rockets? We'll do some question and answer. I've got a couple of things here. I've been kind of like skimming to make sure that there's no technical issues in the comments. But let's see what people say. Oh, okay, so my aunt is watching. And she says she saw the last space shuttle land in Florida, like the last one that ever flew land in Florida, which is pretty cool. I think my mom saw that too. She said she was at the airport and everyone was looking at something and she turned around and it was just the space shuttle coming in. I have never seen the space shuttle in person flying. I mean, I never will because it's out of, it's not flying anymore, but I never saw the space shuttle flying. I have seen it at the Udvar-Hazy Museum in Washington, or I guess that one's in Virginia, which is pretty cool. Kim says there's a great collage video of the SpaceX failures to recover stage 1. There were a lot of them. It took a while, but it's a very difficult problem to solve. Don says, can you talk about why rockets have stages? They have stages because you want to get rid of mass as much as possible. If you were trying to get an empty tank into space, that's kind of useless. As far as, you're going to expend more fuel trying to get that dead weight into space that you're not going to use. And so they wanted to create a way to get rid of that mass if they could. And so stages, solid rocket boosters, things like that, as soon as the tank is empty, it gets dumped. And so that saves having to haul that mass even further. Any other questions about rockets? Also, if you have any suggestions for the next topic, I got a couple of ideas. There's a whole bunch of planets, and someone once wanted exoplanets. Exoplanets are pretty cool. We could do one on exoplanets. Oh, Jersey says, I saw Discovery fly into Dulles Airport. Oh, that's so awesome! Yeah, I love watching rockets. I mean, living in Maryland, it's possible to see. And I've never been to Kennedy Space Center. There's a lot more that flies into there, or launches from there. But if you live in Maryland or Virginia or DC, even as far as like Pennsylvania, New Jersey, Delaware, you might be able to watch a rocket launch at some point from Wallops, which is pretty cool. Have I sent up a rocket? I've been on teams that have sent things up on rockets. My internship when I first arrived at NASA, I guess I haven't really talked about my history at NASA. So I had several internships at NASA before I actually became employed at NASA. And one of my internships was working on a sounding rocket called Visions. It was going to study the Northern Lights, so the aurora. And for part of that, I got to I got to go up to Fairbanks, Alaska, which has a sounding rocket range called Poker Flats. I got to go up there in the middle of February. It was negative 20 degrees out. It was really cold, but I was in the bunker, like right next to where the rocket launched, and I was in the bunker when they counted down and launched and hit the button, and it was really cool. I was only reading temperatures of the instrument, so I was an intern doing intern things. I wasn't pressing the button, but my thing got to go up on a rocket, which is pretty cool. I also work on CubeSats, and so I launched the Firefly, or I helped to develop the Firefly CubeSat, and then I got to go to Wallops and watch that launch. And there's plenty that I haven't watched launch, but I developed some part of the spacecraft and then watched it launch online with the rest of everybody. When is the next rocket to go to Mars? I believe that's the Mars 2020 mission, which is now called the Perseverance rover. I think that's the next one. And to go to Mars, they have to do a couple of weird orbital maneuvers. Don, if you ever want to do one on orbit stuff, feel free. Because I don't know as much about orbital mechanics. I took 2 orbital mechanics classes, but I've never done that personally in my job. But they have to do a couple of weird boost maneuvers and things like that to get out of Earth orbit and into the Martian orbit. All right. Okay, well, if there are no other questions, I am going to, hold on. I am going to go on to the math problem that I have set up. And again, I'm writing backwards. There's things that are backwards. It's because my brain has to flip it. So I might have missed one. And if anyone wants to stick around for the math who isn't in 6th through 12th grade, feel free. But you can leave now if you want. Okay. So for this problem, what I want to do is I want to find the acceleration of a model rocket. Now, these equations can be used for a rocket that's going to space. I think the website that I got this from, they also had an example for, I think it was the space shuttle. And so they had more complicated numbers to work with, but you can actually calculate how much acceleration the space shuttle needs to accelerate out of the atmosphere. This one doesn't leave the atmosphere. As a note, it's a model rocket, so it just goes up and comes down. Okay, so here's a model rocket. And here is the force of thrust. So remember I talked about you push stuff out the back and you get forward thrust. So here's your force that's making you leave the atmosphere, or leave the launch pad. And then the stuff that's holding you back, the force that is working against the thrust, is your weight. So that's the mass times the gravity of whatever planet you're trying to leave. Earth's gravity at the surface of the Earth is 9.8 meters per second squared. 9.8 meters per second squared. So that times your mass is what is holding you back when you're trying to leave the launch pad. There's also drag, but I wanted to kind of keep this simple, so I didn't add in drag. The shape of your rocket body kind of influences how much drag you have. Okay, so we're trying to find acceleration. There's a couple of things that we have to kind of rearrange to get this equation. This is the force, the total force over your mass gives you your acceleration. So in this particular case, we were given some things. We were given that the thrust of this particular rocket, it produces 5 newtons of thrust. Newtons is the standard metric unit for force. Our mass is 50 grams. So the whole thing, fuel included, weighs 50 grams. I'm going to have to convert this to kilograms in order to get it to newtons. So force, total force acting on this rocket, is the thrust minus the weight. If the thrust exactly equaled the weight, you wouldn't go anywhere. So the thrust force has to be greater than your weight. To get weight, I already said, we have our mass of the object times the force of gravity on the planet that you're trying to escape from. In the case of Earth, this is, I forgot the squared, pretend there's a squared there, 9.8 meters per second squared. That's going to bug me. Let me just write 2 backwards here. It's really easy to fit. All right, so 9.8 meters per second squared. The mass, we know it's 50 grams, so we have to convert to kilograms. And you just kind of move the decimal point. So 1, 2, 3. The decimal's here now. We have 0.050 kilograms. And you can do this in your head, or you can use Google, whatever. But a kilogram is 1,000 grams, so you move it 3 decimal points. Together, and you get your weight. 0.49, and we're going to have this weight in newtons because we're using kilogram meters per second squared, which is a newton. The weight is a force. So we have our first variable in our quest to find the force. We have weight, and we were already given the thrust. So now we have both of these 2 variables, we can find the total force acting on this rocket. We have the thrust, which was given to us, 5 newtons, and we have the weight, which we just calculated, 0.49 newtons. And you have 5 newtons minus 0.49 newtons. Plug that into your calculator. You get 4.51 newtons as the total force acting on this rocket. And it's acting in the upward direction. For your acceleration, we just solved for the variable that we didn't have before. Remember, they gave us the mass, and that's how we found our weight. So we're using the force, which we just calculated, and dividing that by the mass, which they gave us, in kilograms. And we're getting the acceleration. So we have 4.51 newtons divided by 0.050 kilograms. And your acceleration, if you divide that by that, is 90 meters per second squared. What this means is your velocity is increasing by 90 meters per second every second. Imagine how quickly you might be going after, I don't know, 10 seconds. But you don't have an endless supply of fuel. So even though your model rocket, if you had, an endless supply of fuel that magically didn't weigh anything, you could keep going to space. In reality, you may only have room for 1 second's worth of fuel. And that fuel weighs, I don't know what percentage of 50 grams that is, maybe 40 grams of it is your fuel. And so you can only jam that much into a tiny little amount of mass. That doesn't make any sense. That tiny rocket body only has so much mass, and that mass has, a second's worth of fuel. And so even though you're increasing your velocity very quickly, it's over in a second, and then you drop back down to the ground. So in rocket equations, people have to calculate very carefully, and it's kind of an iterative process. They have to calculate very carefully how much energy is stored in their fuel for the amount of weight that they can carry with the amount of energy that they're getting from their fuel. And so that's part of the reason why your payload is, it's called a payload, but the thing that you're carrying into space is such a small amount of your total rocket, is because it takes a lot of fuel for a long time, several minutes, to get up into orbit. And the entire time you're trying to drop any weight that you can, which is why you have things dropping off of your rocket as like first stage, second stage, that type of thing. Okay, so we've solved our math equation. If you have any other questions, feel free to leave it in the comments after the video is over. I'm going to be posting this to my YouTube channel. And I'm also going to be posting some links to different resources that I found on rockets. And also the link to the page where I got this. So if you want to try calculating for the space shuttle, you can have one that kind of guides you through it. Okay, thank you so much for joining me, and I'll see you guys later. Bye.